In this video, let's form differential equations of a family of ellipses having foci on y-axis and center at the origin. So the ellipses would look something like this. In a separate video, we have calculated differential equation for ellipses with foci on x-axis. Watch that and compare if the differential equations will be any different or will they be same. So let's start calculating this. We know that equation of an ellipse having foci on y-axis is given as x square upon b square plus y square upon a square equal to 1, where a is the distance from 0 to the end of the ellipse. So we have two arbitrary constants here and we need to eliminate these two to get the differential equation. So the differential equation will be of the order of 2. So let's start differentiating. So let's differentiate 1. Differentiation of x square, which will be 2x, and 1 by b square is a constant, so that will be written as it is. Differentiation of y will be 2y dy by dx, and a square will remain as it is, equal to 0. Since 2 is there in all the terms, we can cancel it out and be left with x upon b square plus y upon a square dy by dx equal to 0. Let's call this equation number 2. Let's differentiate equation number 2 and see what we get. So differentiating 2. Differentiation of x is 1 and b square will remain as it is plus 1 by a square, and we need to differentiate y into dy by dx. We will differentiate y into dy by dx by the identity used to differentiate the functions in multiplication. So if we need to differentiate two functions u and v which are in multiplication, we differentiate it using first function into differentiation of second function plus second function into differentiation of first function. So here let us call y as the first function and dy by dx as the second function and use this identity to differentiate. So we are going to get 1 upon b square plus 1 upon a square into first function y into differentiation of second function. So differentiation of dy by dx will be differentiation of second order. So d square y upon dx square plus second function, which is dy by dx, into differentiation of first function, which is differentiation of y, which will be dy by dx equal to 0. From this equation, let us calculate the value of 1 plus b square. So we will get, from this equation, let us calculate the value of 1 upon b square. So we are going to get 1 upon b square as minus 1 upon a square into y into d square y dx square plus dy by dx whole square. And call this equation number 3. Now we can substitute equation number 3 in equation number 2. We have calculated the value of 1 upon b square. Let us see what we get after substitution. So I am going to get x into 1 upon b square, which is minus 1 upon a square into y into d square y upon dx square plus dy by dx whole square y upon a square dy by dx equal to 0. Let's simplify. So we have got 1 upon a square in both the terms. So let's take it common so that we can cancel it out. So I want to write 1 upon a square, and let's write the positive term first. So I can write y into dy by dx minus xy d square y upon dx square minus x into dy by dx whole square. equal to 0. Since 1 by a square is in multiplication, this will cancel out and we will be left with y into dy by dx minus xy d square y upon dx square minus x into dy by dx whole square equal to 0. You can either stop here or we can go one step further to bring the highest order derivative into positive. So we can write xy d square y upon dx square minus plus y dy by dx whole square minus y dy by dx equal to 0. And this is the final differential equation for family of ellipses having foci on the y-axis. So does this equation look any familiar to you? I will put a link in the I button and at the end of the video where we have calculated equation for hyperbolas. So that equation and this equation is exactly the same. Watch that video to see how we get the same result after eliminating the arbitrary constants. Keep practicing. Let's meet in the next video.